tangent line problem is a rate of change problem. Now in the past I've solved rate of change problems by using the slope formula. I'm given 2 points, I find the average rate of change between those 2 points. Now what makes the tangent line problem distinct from a regular slope problem is that it only has 1 point. So I can't use the regular slope formula to do a tangent line problem because it only has 1 point. y2 minus y1, x2 minus x1. I'm going to have an x1 and a y1 or an x2 and a y2. I'm going to be missing one of them. So I can't really use it in the way that I've been approaching problems in the past. But suppose that someone were to ask me to at least have a guess. Said, well, if you can't use that, then guess anyways. What would my guess be? Well, I couldn't really just look at it and guess, but what I could do is say, here's my point, and this point is 1, 1, 1. And the function is f of x is equal to x squared. What I might tell that person is say, well, I can't give you the instantaneous rate of change at 1, 1, but what I can do is pick a point that's very, very close. What I might pick is 1.0001 and then put that in the function, and then I get some y, and then find the slope between those 2 points. Now while that isn't the exact rate of change at point 1, it'll be damn close, won't it? So that's what I've done in this chart over here. I've gone ahead and picked 1, 1 as one of my points. That is the point that I'm wanting to find the approximate rate of change. And then I just started plugging in points into this formula. So I plugged in 2 squared is 4, and then I found the rate of change between these two. And you get 2 minus 1, 3, 1, 2 minus 1, which is 1, so it's just 3. And I do it for 1.5, and then 1.1, 1.01, 1.001. And if I look at the slope as I put these into the formula, it goes from 3 to 2.5 to 1.9 to 1.99 to 1.999. And that is approaching it from the right hand side. So I started with 2, and I started getting closer and closer and closer to 1 until I was 0.001 away. And if I put 1.0001, I'll continue getting 1.99999. As soon as I keep getting closer, it's 1.999, just keeps getting closer and closer. And the same thing when I approach from the other side. If I start at 0, I get a slope of 1. If I go to a half, I get a slope of 1.5, 0.9, 1.9, 0.99, 1.99, 0.999, 1.999. So I'm looking at these values, and they seem to be getting closer and closer to 2. While they're not becoming 2, they seem to approach a value of 2, and this is where limits are going to come in the next section. And that exact value, the instantaneous rate of change, that is called a derivative. That's basically what a tangent line problem is. A tangent line problem is a derivative. A derivative is an instantaneous rate of change. And that is basically what the first half of calculus is all going to be about. Actually, that's probably what the first 1/3 of it is going to be about. Then the second third of it is going to be about integrals, which is calculating volumes and areas and stuff. And then the third part is going to be doing those two things, so derivatives and integrals, but in more than one dimension. But this is the basic idea. This is basically the first big problem, and this is basically the subject of calculus right here. Is integrals and tangent line problems. And a tangent line problem is just trying to find the rate of change at a specific point in time. And what is going to happen is that they're going to continue on further. They're going to take this idea of, okay, well, we can't figure out what the point is exactly right there, but I can get infinitesimally close to it. That's going to lead into limits, and then once we can prove that there's a limit here, then we can say, well, the derivative, the instantaneous rate of change, is such and such, and that's what is going to lead into derivatives, and then from there on,